Imagine looking up at the sky. You might see the sun, the moon, or a tapestry of distant stars, but there is something else there, something entirely invisible to our eyes. It is a vast protective bubble that surrounds our planet. This bubble is called the magnetosphere, and it is generated by the molten iron core deep within the Earth. It acts like a giant, invisible shield, a guardian against a constant storm raging through space. This storm is not made of wind or rain as we know it. It is a relentless stream of charged particles flowing outwards from the sun, a cosmic gale known as the solar wind. Without our magnetosphere, this solar wind would strip away our atmosphere, leaving Earth a barren and lifeless rock, much like Mars. This invisible shield is not a static, solid wall. It is a dynamic, shimmering field of energy that is constantly pushed and pulled by the solar wind. Think of it like a flag fluttering in a strong breeze. The side facing the sun is compressed and pushed inwards, while the side facing away from the sun is stretched out into a long comet-like tail that extends for millions of kilometers into space. This constant interaction creates a complex and turbulent environment, a battleground of cosmic forces right above our heads. It is a place of immense energy where particles are accelerated to incredible speeds and magnetic fields twist and snap in a process called magnetic reconnection. Understanding this region is fundamental to understanding our place in the solar system. This cosmic dance between our planet's magnetic field and the sun's outpouring is not just a curiosity for astronomers, it has real-world consequences. When the solar wind is particularly strong during events like solar flares or coronal mass ejections, it can buffet our magnetosphere with incredible force. This can induce powerful electrical currents in our atmosphere and even on the ground. These space weather events can disrupt our satellites, interfere with GPS signals, and even threaten to overload power grids. So, you see, this invisible battle happening hundreds of thousands of kilometers above us is directly connected to the technology that powers our modern civilization. It's a profound connection between the vastness of space and our daily lives. For decades, scientists have strived to understand the intricate details of this interaction. We have sent probes and built telescopes to study this region, but much of it has remained a mystery. The processes at play happen incredibly fast and on very small scales, making them difficult to observe. It is like trying to photograph a single hummingbird's wing beat during a hurricane. But science is a story of persistence, of developing new tools to peer deeper into the unknown. And recently, a remarkable mission has given us a new set of eyes, allowing us to witness the intricate details of this cosmic battlefield in a way we never could before, revealing surprises that challenge our long-held ideas about how the universe works. To unravel the secrets of the magnetosphere, you need a very special kind of tool. You can't just send one spacecraft. The phenomena are too complex and happen too quickly. NASA's answer to this challenge is a truly brilliant piece of engineering called the Magnetospheric Multiscale Mission, or MMS for short. This isn't a single probe but a team of 4 identical spacecraft flying in a precise formation. They orbit the Earth together, moving through the invisible boundaries of our magnetic shield. Think of them as a team of synchronized dancers, perfectly choreographed to measure the space around them in 3 dimensions. This formation allows them to capture events with unmatched precision. The primary goal of the MMS mission is to study a fundamental process called magnetic reconnection. This is what happens when magnetic field lines from the sun collide with Earth's magnetic field lines. They break apart and then violently reconnect, releasing an enormous amount of energy. This process is one of the most important drivers of space weather. It is what fuels the beautiful auroras, the northern and southern lights, but it is also what can trigger the technological disruptions I mentioned earlier. MMS was designed to fly right through these reconnection events and measure the particles and fields with incredible speed, thousands of times a second, to understand exactly how this energy is released. Each of the 4 MMS spacecraft is an octagonal prism, packed with state-of-the-art instruments. They are like flying physics laboratories. They have sensors to measure the magnetic and electric fields with exquisite detail. They also have detectors that can count and identify the different types of particles that make up the solar wind and the plasma within our magnetosphere. By flying in a tight, pyramid-like formation, they can distinguish between changes happening over time and changes happening across space. This is crucial. It allows scientists to build a full, 3-dimensional picture of the plasma physics at play, something that was impossible with earlier single spacecraft missions. The mission has been a spectacular success. Since its launch in 2015, MMS has given us an unprecedented view of the universe on its smallest, fastest scales. It has broken records for the fastest GPS signal in history, using its own sensors to track its position with incredible accuracy. But beyond the technical achievements, it is the scientific discoveries that are truly transformative. The data sent back by these 4 sentinels has allowed us to witness the intricate dance of particles and fields up close. And in doing so, MMS has stumbled upon something entirely unexpected, a new piece of the puzzle that is forcing us to rethink our understanding of the space right on our own cosmic doorstep. To understand the new discovery, we first need to appreciate the nature of the solar wind itself. The sun is not just a quiet ball of light in the sky, it is a star, a gigantic nuclear furnace. Its outer atmosphere, the corona, is incredibly hot, reaching temperatures of millions of degrees Celsius. At these extreme temperatures, the sun's gravity can no longer hold on to all of its material, so it constantly sheds a stream of particles into space. This stream is made mostly of protons and electrons, the building blocks of atoms. This outflow is the solar wind. It blows away from the sun in all directions, filling the entire solar system. This is not a gentle breeze. The solar wind travels at astonishing speeds, typically around 400 kilometers per second, which is about 1 million miles per hour. Sometimes, when the sun is more active, it can travel even faster. This wind carries with it the sun's magnetic field, stretching it out through space to create what is known as the interplanetary magnetic field. As it travels outwards, it interacts with everything in its path: planets, moons, comets, and asteroids. It is the dominant force shaping the space environment of our solar system, the medium through which all the planets travel. It is the very breath of the sun. Here on Earth, as we've seen, we are largely protected from the direct blast of the solar wind by our magnetosphere. This shield deflects the bulk of the charged particles, forcing them to flow around our planet like water around a boulder in a stream. But some of that energy and some of those particles do manage to leak in, especially near the magnetic poles. This is what gives rise to the stunning displays of the aurora. The interaction is a constant push and pull, a transfer of energy from the sun to the Earth's environment. Understanding the properties of the solar wind, its speed, its density, its magnetic field, is therefore crucial for predicting space weather. For a long time, scientists thought of the solar wind as a relatively uniform, though turbulent, flow of particles originating solely from the sun. We built our models based on this idea. We assumed that by the time it reached Earth, it was a pure sample of the sun's corona, a pristine stream of solar material. This assumption made sense, as it's a long journey from the sun to our planet. We believed that any other material it might pick up along the way would be insignificant. But as is so often the case in science, when we look closer with better instruments, the universe reveals a complexity we had never imagined. Now let's add another character to our cosmic story. As the solar wind flows out from the sun, it doesn't travel through a complete vacuum. Space is incredibly empty, but it's not entirely empty. It contains stray atoms of gas. These atoms can come from many sources. They can be interstellar gas from outside our solar system that has drifted in. Or they can originate from within our solar system, perhaps from the atmospheres of planets like Earth or Mars, or from the ice vaporizing off a passing comet. These atoms are neutral, meaning they have no electrical charge. Because of this, they are invisible to the magnetic fields of the solar wind and can drift freely. So, you have these neutral atoms floating peacefully in space. Then along comes the super-fast solar wind. As these neutral atoms are bathed in sunlight, the ultraviolet radiation can knock an electron off them. This process is called ionization. Suddenly the atom is no longer neutral. It now has a positive electrical charge, and it becomes what scientists call an ion. Because it has been picked up by the solar wind environment, it's given a special name, a pickup ion, or PUI for short. It has gone from being an indifferent bystander to an active participant in the cosmic dance. Once an atom becomes a pickup ion, its life changes dramatically. It is no longer free to drift as it pleases. It is now electrically charged, so it immediately starts to feel the force of the magnetic field carried by the solar wind. It gets grabbed by this field and is instantly accelerated, swept along with the fast-moving flow of solar wind particles. Imagine standing still and suddenly being scooped up by a river flowing at 1,000,000 miles per hour. This is what happens to a pickup ion. It is a violent transition, and these newly born ions are injected into the solar wind with a huge amount of energy. Scientists have known about pickup ions for a long time. They are an expected part of the physics of the heliosphere, the giant bubble created by the solar wind that envelops our solar system. We have observed them far out in the solar system, where the solar wind slows down as it meets the interstellar medium. We thought that near Earth the solar wind was so fast and so dense that the number of pickup ions would be tiny, almost insignificant. They were considered a minor ingredient, a bit of background noise that wouldn't have any major effect on the overall behavior of the solar wind. This was a reasonable assumption, but it turns out to be wrong. The 4 MMS spacecraft were doing what they do best, flying through the boundary of Earth's magnetosphere. They were specifically looking at a region called the bow shock. This is the area where the solar wind, traveling at supersonic speeds, first encounters Earth's magnetic field and abruptly slows down, creating a shock wave, much like the bow wave created by a boat moving through water. It is a region of immense turbulence and complexity. The MMS instruments were taking their ultra-fast measurements, capturing the chaos in exquisite detail. And as scientists analyzed this data, they noticed something that shouldn't have been there. They saw waves. These weren't just any waves, they were specific high-frequency ripples in the magnetic field. They were oscillating very rapidly, and they were propagating upstream against the flow of the solar wind. This was strange. The solar wind is moving so fast that it's very difficult for anything to travel against it. It's like trying to swim up a powerful waterfall. The team, led by Dr. Hui Zhang at the University of Alaska Fairbanks, looked closer at the data. They analyzed the particles at the exact moments these waves appeared. What they found was a direct, undeniable link between the waves and the presence of pickup ions. The data from MMS was so precise that it allowed the scientists to do something remarkable. They could see that these newly created pickup ions, specifically helium ions that originated from interstellar gas, were not just being passively carried along. As they were energized and began to gyrate around the magnetic field lines, they were generating these waves. They were actively disturbing the solar wind around them. The energy they gained when they were picked up was being released back into the plasma in the form of these magnetic waves. The pickup ions were not just passengers, they were shaking the bus. This was a stunning revelation. The discovery showed that even a very small population of pickup ions, just a tiny fraction of the total particles in the solar wind, could have a dramatic and measurable effect. They were creating a new source of energy and turbulence in a region where scientists thought everything was dominated by the sun alone. It was as if we had been listening to an orchestra for decades, thinking all the sound came from the main stage, only to discover a small group of musicians in the audience playing their own powerful tune, a tune that was changing the acoustics of the entire hall. This discovery is so surprising because it goes against the standard model of the solar wind near Earth. For decades, our models have treated the solar wind in this region as a collisionless plasma. This means we assumed the particles were so spread out that they rarely, if ever, bumped into each other directly. In this view, all the energy and turbulence were thought to come from large-scale forces, like the interaction with Earth's bow shock. The idea was that any small-scale effects like those from a few pickup ions would be quickly smoothed out and disappear into the overwhelming flow of the solar wind. The MMS findings turn this idea on its head. They show that pickup ions act as a significant localized source of energy. When a neutral atom is ionized, it is injected into the solar wind with a lot of free energy. It is not moving in harmony with the other particles. This extra energy has to go somewhere. What this new research demonstrates is that one way the plasma gets rid of this excess energy is by generating these high-frequency waves. This is a fundamental process of energy transfer that was happening right under our noses, but we simply didn't have instruments sensitive enough to see it until now. The fact that these waves were found just upstream of the bow shock is also profoundly important. The bow shock is where the solar wind is first heated and slowed as it interacts with Earth. The physics of this shock wave is incredibly complex, and scientists have long worked to understand exactly how the energy of the solar wind is dissipated there. The standard models assumed that the solar wind arriving at the shock had a certain set of properties, but this discovery shows that the solar wind is already being preconditioned or modified before it even reaches the shock. The pickup ion waves are adding extra energy and turbulence into the system. This means that our understanding of the bow shock itself may be incomplete. It's like trying to understand how a dam withstands a river without knowing that there are powerful springs bubbling up right in front of it, changing the river's flow and force. These waves generated by the pickup ions could be contributing to the initial heating of the solar wind particles, changing the fundamental physics of how the shockwave works. It introduces a new mechanism of energy transfer that our models had not accounted for, forcing a major re-evaluation of one of the most fundamental interactions in our corner of the cosmos. The implications of this discovery ripple outwards, much like the waves themselves. Our computer models of the space environment around Earth are incredibly sophisticated, but they are all built upon a set of fundamental assumptions about the physics involved. One of those assumptions was that the solar wind arriving at Earth was a pristine flow from the sun. This new finding proves that assumption is not quite right. The solar wind is being actively modified on its journey, with pickup ions acting as a hidden source of energy and turbulence. This means our models need to be updated. Scientists who build these complex simulations will now have to incorporate this new physical process. They will need to add the effects of pickup ions and the waves they generate. This is not a simple tweak. It involves adding a new layer of physics that connects the smallest scales, the behavior of individual ions, to the largest scales, the overall structure of the bow shock and magnetosphere. The goal will be to see how this new ingredient changes the outcome of the simulations. Do the models now better predict the location and strength of the bow shock? Do they more accurately represent how energy is transferred into Earth's magnetosphere? This could have a direct impact on our ability to forecast space weather. Accurate space weather prediction is vital for protecting our satellites, power grids, and astronauts in space. If our models have been missing a key piece of the energy budget, it could explain why some predictions are not as accurate as we would like them to be. By including the energy from pickup ions, we might be able to build more robust and reliable forecasting tools. It could help us better understand and predict how much energy from a solar storm will actually make it past the bow shock and into the Earth's environment. Beyond Earth, this discovery has implications for our understanding of other planets in the solar system. Planets like Mars and Venus, which have very weak or no global magnetic fields, interact with the solar wind much more directly. Pickup ions created from atoms escaping their atmospheres are known to play an even more significant role in the space environments of those planets. The discovery that these ions can generate powerful waves provides a new mechanism to explain how these planets lose their atmospheres to space over billions of years. It's a piece of the puzzle that could apply across the entire solar system. The beauty of a discovery like this is that its importance extends far beyond our own solar system. The universe is filled with plasma, the same state of matter that makes up the solar wind. Plasmas are found in the swirling accretion disks around black holes, in the vast nebulae where new stars are born, and in the colossal explosions of supernovae. In all of these environments, shock waves and the interaction of different particle populations are fundamental processes. The physics that MMS has uncovered in our own backyard is a microcosm of the physics that governs the cosmos on its grandest scales. For example, astronomers study supernova remnants, the expanding shells of gas from an exploded star. These shells slam into the surrounding interstellar gas, creating massive shock waves. These shocks are thought to be the primary accelerators of cosmic rays, which are extremely high-energy particles that travel across the galaxy. The process of how particles get their initial energy boost at these shocks is still a major puzzle. This new finding about pickup ions generating waves that heat a plasma provides a tangible, observable mechanism that could be a crucial part of that cosmic ray acceleration process. By studying these processes near Earth, where we can actually send spacecraft to take direct measurements, we are conducting a grand cosmic experiment. The space around our planet becomes a natural laboratory. We can test our theories about plasma physics here in detail, and then apply that knowledge to situations light years away that we can only observe with telescopes. Understanding how pickup ions transfer energy into the solar wind helps us build better models for how similar processes might work in the extreme environments around distant stars and galaxies. It's a wonderful example of how exploring our local neighborhood helps us understand the entire universe. This connection highlights the profound unity of the laws of physics. The same fundamental principles that cause a tiny helium ion to create a ripple in the magnetic field near Earth are at play in the most dramatic and energetic events in the cosmos. It's a humbling and awe-inspiring thought. Every new detail we uncover about our own space environment adds to the great tapestry of our cosmic understanding. It reminds us that even the seemingly empty space between the planets is a dynamic and complex place, filled with invisible processes that are clues to the workings of the universe itself. This discovery by NASA's MMS mission is a perfect illustration of how science works. We build a theory based on our best observations. We design a mission to test that theory, and sometimes, if we are lucky, the mission reveals something completely new that sends us back to the drawing board. This is not a failure, it is the very heart of progress. It is the thrill of finding a new continent on a map we thought was complete. The discovery of these pickup ion waves has opened up a new avenue of research, posing more questions than it answers, which is the hallmark of a truly great discovery. The immediate next step for scientists is to comb through more of the MMS data. The mission has been observing for years, and there is a vast archive of measurements to explore. Researchers will now be looking for these wave signatures in different regions of space and under different solar wind conditions. Are these waves always present? Are they stronger when the solar wind is faster? Do different types of pickup ions like those from Earth's own atmosphere create different kinds of waves? Each answer will add another layer of detail to this new and developing picture of our space environment. Looking further into the future, this finding will undoubtedly influence the design of new missions. Future spacecraft sent to study the Sun, other planets, or even to venture into interstellar space will be equipped with instruments capable of detecting these subtle interactions. Scientists will want to measure the properties of pickup ions and the waves they generate throughout the solar system to build a complete global model. This discovery provides a clear scientific target, a new phenomenon to be mapped and understood, driving the next generation of exploration and pushing the boundaries of our technology. In the end, this is a story about the power of curiosity. It's about our innate desire to understand our place in the universe. We live on a small, fragile planet, shielded from the cosmos by an invisible magnetic field. For centuries we have looked up and wondered. Now, with missions like MMS, we are no longer just wondering. We are reaching out, measuring and beginning to understand the intricate and beautiful physics that govern our cosmic home. And with every new discovery, no matter how small it may seem, the universe becomes just a little bit less mysterious and a whole lot more wonderful.